On the night of July 9, 1958, in the remote Lituya Bay of Alaska, the Earth unleashed a wave of impossible scale. It wasn't just a large wave, it was a liquid wall that surged 1,720 feet high, taller than any skyscraper standing on the planet today. This colossal surge of water did not simply flood the landscape. It acted like a sandblaster, scouring entire hillsides of their ancient forests, stripping soil and rock down to the bedrock. The sheer physics of the event defied everything known about ocean waves, leaving behind a stark line of devastation that scientists would study for decades. It was a geological event compressed into a few terrifying minutes. To understand this raw power, we must first look at the stage itself, the fjord. A fjord is a deep, narrow, U-shaped inlet of the sea, carved into the land by the immense weight and grinding force of a glacier during an ice age. When the ice retreated, the ocean flooded in, creating a unique geological feature. The key to a fjord's volatile nature is its geometry. The walls are incredibly steep, often plunging almost vertically into the water. This creates a confined, deep channel. This specific shape, a product of ancient ice, is the perfect vessel to contain and amplify the energy of a sudden, violent displacement. The trigger for the Lituya Bay event was a magnitude 7.8 earthquake along the nearby Fairweather Fault. But this powerful tremor did not create the wave directly, as a typical undersea earthquake might. Instead, it was the catalyst. The shaking acted like a colossal hammer blow to an already unstable mountainside overlooking the bay. In an instant, the earthquake dislodged an immense block of rock, ice, and soil. The scale is difficult to comprehend. 40 million cubic yards of material, weighing an estimated 90 million tons, broke free from the mountainside and began to fall. An entire piece of a mountain was suddenly airborne. This raises the central scientific mystery. How can a landslide, even a massive one, generate a wave so much taller than those created by the most powerful tectonic tsunamis? An undersea earthquake displaces the entire seafloor over a vast area, yet its waves are rarely this tall at their source. The answer lies in a different kind of phenomenon. This was not a tectonic tsunami. It was an impulse wave, a term for a wave generated by a sudden concentrated impact. Think of it not as a gradual lift of water, but as a violent, instantaneous shove, like a paddle striking the water with immense force. The physics begin with the mountain itself. The 90 million ton rock mass was perched approximately 3,000 feet above the bay. In this position, it held an enormous amount of stored energy. This is gravitational potential energy, energy an object has because of its height. As the rock slab fractured and fell, that immense potential energy was converted into kinetic energy, the energy of motion. The mass accelerated under gravity, gathering speed and momentum with every foot it dropped. It was no longer just a piece of a mountain, it was a projectile of unimaginable force, aimed directly at the constrained waters of the fjord. In an instant, the mountain's immense potential energy, the energy of position, stored over millennia, was converted into kinetic energy. This is the energy of motion. The result was an explosive release of force, equivalent to a major earthquake, all directed into a narrow, unyielding body of water. This is where the scale becomes almost incomprehensible. The initial colossal wave that is so often cited was not the wave that traveled down the bay. It was a splash-up. Think of a stone dropped into a narrow glass. The water has nowhere to go but up. That 720-foot mark was the height the water surged up the steep mountainside directly opposite the landslide. A vertical jet of displaced water, rock, and air, flung skyward by raw physics. It scoured the mountainside clean to the bedrock, leaving a permanent scar that testifies to the power of the initial impact. Now we shift focus to the main wave. This was the body of water that propagated out from the impact zone. Here, the fjord's unique geology created a terrifyingly efficient delivery system for destruction. The steep, U-shaped valley acted as a wave guide. Unlike in the open ocean, where a wave's energy radiates outward and dissipates over distance, the fjord's sheer rock walls contained it. The energy was channeled, it was focused. Every joule of force from the landslide was funneled directly down the length of Lituya Bay. The consequence of this waveguide effect is a wave that retains its destructive power. It cannot weaken by spreading out. Instead, it is forced to travel as a concentrated pulse of energy, a liquid battering ram moving through a perfect barrel. But this event revealed a counterintuitive property of such waves. They are incredibly fast, yet they are not deep ocean travelers. The Lituya Bay wave was estimated to be moving at over 100 miles per hour. That is faster than a hurricane's winds. So a crucial question remained. Why did this immensely powerful, fast-moving wave exhaust itself within the bay? Why didn't it continue into the Gulf of Alaska as a catastrophic tsunami? The answer lies in its fundamental structure, which is radically different from an earthquake-generated wave. The scientific revelation was this. A landslide-generated wave is not a clean, oscillating ripple of energy. It is a turbulent bore. Because its wavelength, the distance from one crest to the next, is very short, all its energy is packed into a chaotic, near-vertical wall of water. This is not the graceful wave of the open ocean. It is a grinding, debris-filled horror. It carries the mountain with it. A churning mass of water, rock, sediment, and entire trees, moving as one unstoppable force, scouring the fjord floor as it travels. This churning, chaotic mass of trees, rock, and ice was more than a wave. It was a liquid grinding tool. As the bore propagated down the fjord, it scoured the bedrock on the sides and floor. It fundamentally and permanently altered the underwater topography in a matter of minutes. This abstract power becomes terrifyingly real when viewed from the water's surface. 2 fishing boats were anchored in Lituya Bay that night. One, crewed by Howard Ulrich and his young son, was suddenly caught in the grip of forces beyond comprehension. Their anchor lines snapped like thread. They were not merely lifted, they were propelled upward on the face of that impossible wave. The boat was carried, impossibly, over the spit of land at the bay's entrance and into the Gulf of Alaska. They looked down from the crest of the wave and saw the tops of trees below them. This grounds an immense scientific truth. We often think of geological change as an impossibly slow process. Erosion carving a canyon over millennia, continents drifting apart over eons, the planet's work unfolding on a timescale far beyond human life. But Lituya Bay reveals another side of geology. It is a testament to the fact that catastrophic, landscape-altering change can happen in a heartbeat. The work of thousands of years of erosion, accomplished in less than 5 minutes. This event shifted our understanding and spurred a new scientific frontier. Today, scientists actively monitor similarly unstable mountainsides in fjords around the world. At sites like Åkerneset in Norway, an entire mountainside is slowly, but measurably, sliding towards the water. The goal is prediction. An arsenal of technology is deployed to watch for the slightest acceleration. Ground-penetrating radar maps internal cracks. Laser scanning, or LiDAR, detects surface changes with millimeter precision. GPS sensors track the slow, relentless creep of the rock, providing an early warning system for the inevitable. Yet, this power is not merely destructive, it is profoundly creative. The same immense forces that can trigger such a devastating event are precisely the ones that sculpted these breathtaking landscapes in the first place. The incredible power of glacial carving, the relentless force of tectonic uplift that raised the mountains, the fundamental law of gravity that pulls them down. They are all part of the same planetary engine. Lituya Bay wasn't an anomaly. It was a raw, unfiltered expression of the Earth's dynamic and ever-changing character. The event at Lituya Bay was not an ending. It was a benchmark, a stark demonstration of physics at a planetary scale, now serving as a critical data point for scientists monitoring other vulnerable coastlines around the globe. The forces that unleashed that wave are not dormant. They are active, and they are being watched. We move from the past to the present, to the fjords of Norway. Here, another factor accelerates the risk: a warming climate. High on these steep slopes, ancient ice and frozen soil, known as permafrost, have acted like geological glue for millennia. This frozen mortar holds fractured rock together. But as temperatures rise, that glue is melting. Consider the mountain known as Åkerneset. A massive fissure, hundreds of meters long, widens each year. Over 50 million cubic meters of rock are slowly, unstoppably sliding towards the fjord below. That is a volume of material that could bury a city. The movement is tiny, just a few centimeters a year, but it is relentless. This raises a profound scientific question. How do you measure the slow-motion breathing of a mountain on the verge of collapse? The answer lies in a network of extraordinary technology. Instruments are drilled deep into the rock, listening for the faintest groans of shifting stone. GPS sensors track surface movements with millimeter precision. Lasers and ground-based radar constantly scan the unstable rock face. These systems paint an invisible digital grid across the mountain. They measure the distance to thousands of points every few minutes. Any deviation, any bulge or slip is detected instantly, creating a real-time map of the mountain's decay. From orbit, the perspective shifts. Satellites use a technique called interferometric synthetic aperture radar, or INSAR. They bounce radar signals off the slope from space, recording the returning waves. By comparing images taken days or weeks apart, INSAR can reveal subtle, widespread deformation across the entire mountainside, patterns invisible from the ground. This immense scientific effort is not just an academic exercise, it is a race against gravity. Sophisticated computer models, calibrated with the data from Lituya Bay, have simulated the consequence of the Åkerneset collapse. The resulting wave would be catastrophic, reaching heights of over 80 meters as it funnels through the narrow Storfjorden. The work here reveals a deeper truth about our planet. We are learning to interpret its subtle warnings. The faint, seismic tremor, the creeping fissure, the melting of ancient ice, these are not isolated events. They are symptoms of a dynamic Earth, a planet constantly reshaping itself through immense and powerful processes. This leads to the next frontier in geoscience, moving from monitoring to true forecasting. Scientists are building predictive models that integrate weather data, meltwater flow, and small earthquakes. The goal is to identify the final trigger, the combination of factors that could turn a slow creep into a sudden, colossal failure. The raw power witnessed in Lituya Bay is a permanent part of our world's geological character. Understanding it is not about taming it, but about learning to live with respect for its scale. It is a story written in rock and water, a reminder that the most profound changes on Earth can happen in the blink of a geological eye.